Okay, hey everyone, welcome to Neurosymbolic Wednesdays. Are you seeing my slides?
Not yet.
Okay, great.
Alex, please make full screen.
Yes.
Yeah.
Yeah, good?
Yes. Thanks.
Okay, great. All right, so welcome back to Neurosymbolic Wednesdays. This should be starting to become a habit, your Wednesday technical habit. So today we're fortunate to have Luis. Luis is on the board of the Centaur AI Institute and uniquely qualified to talk about an overview of Neuro-Symbolic AI, of which he was one of the pioneers. And his background, he's now leading research at Catholic Tech. Was educated at Imperial College and MIT. And these slides will be available. Go into the details. You can ask questions in anywhere, basically, Discord, YouTube, or LinkedIn. They'll all get funneled here. And just a heads up about the next week. So we'll sort of a natural follow-on to what Luis will talk about. We'll get into the software frameworks, the major software frameworks out there right now for Neurosymbolic AI. And we'll have Parisa take us through that. Okay, and as usual, these are all the places to connect if you haven't connected in to some of these yet. The crucial one being Discord. So please, if you have only one of these to remember, it's that one. Get on there and you can ask anything about the other ones. That's where the community lives, and that's where we'll have discussions and primarily where you post questions and so on. Okay, and heads up about our learning site, which is coming soon. We'll have all of these videos. And you'll see other ways to participate in our community on the website. Let me just highlight one in particular that we're ramping up now. This is our answer to the current kind of protocols out there being developed around LLMs and for the Neurosymbolic community. So in particular, people interested in programming languages and systems, this is where the action is in developing an agentic protocol for Neurosymbolic. So, and star us on GitHub. Ask Ken, who you'll all see on Discord once you're on there. And just a few things about working with us. Some of the topics I'll just flash here if you're interested in research. Okay, and we're also hiring and so on. And if you have a startup, a Neurosymbolic startup, you want some visibility, let us know. Of course, if you want to donate, we're very ecstatic. Okay, with that, maybe I'll pass it to Luis.
Thank you, Alex. I'm going to share my screen. Just tell me if everything is good. Can you see my screen?
Yes.
Yes? Okay. So I'm going to start. So thank you, everyone. Thank you for the introduction. It's a pleasure to be here. And this talk, as Alex mentioned, is an overview of Neuro-Symbolic AI. I bring some historical perspective, some basic concepts, why integrating learning and reasoning in a methodological way is relevant. some approaches and applications of neurosymbolic AI that now people are talking about these days, where the field is in the news. Corporations have adopted the field, and also some future perspectives in terms of research, technology, and development. So for those who are very new to the field, new to the area, there is always someone in the talk that has not seen it. I recommend those two literature reviews. One of them is from a group mostly from UC Santa Cruz, and it's a very good survey from in terms of technical points to the literature. The second point, it's a different way of seeing the field by Artur and myself, because we analyze how the field has evolved and the way that we see how the field is moving forward. So what questions AI is trying to answer, and why Neurosymbolic is going to be relevant here? So the big question is, can digital machines think? And I believe that all these questions about AGI, about scenarios where AI take over, they stem out of this fascination that we have about building thinking machines or computing machines that can display some sort of intelligence, some sort of cognitive ability that's akin to the ones that we show as humans. And I checked, of course, like, perhaps 90% of the people who use computers, they go in and ask a computer, okay, let's see if this Gemini, the latest model from Google DeepMind, is neurosymbolic. So they are not there yet. Even Gemini says, well, we are not purely neurosymbolic. So the research questions are still open, not there yet. So we have to go back to the hard work. That's where Neuro-Symbolic AI comes from. So forgive me for my initial joke. I'm very bad at jokes because I used to be a nerd. So bad jokes. Let's continue with the talk. So early Neuro-Symbolic AI, several researchers have already noticed and mentioned it in their talks. I'm not the first one to mention it, that perhaps even the first paper on neural networks that was called A Logical Calculus of Ideas Immanent Nervous Activity by McCulloch and Pitts. It's a very famous paper, highly cited. It was already a neurosymbolic paper because they were trying to identify and represent and understand how logical reasoning operations were represented in their initial model of neural networks. That, of course, does not have a perfect correspondence with the biological reality. Another point that we can perhaps raise in the literature was already in the 50s, people like Stephen Klein was a pioneer of computability theory, formal languages, and other fields that are relevant to theoretical computer science. He was already asking himself in a very well-known paper, that very highly cited paper by Klein, to what kind of events can a McCulloch-Pitts nerve net respond by firing a certain neuron. So he was trying to understand, if he's trying to understand the order of events, Klein was a logician, remember, he was trying to understand what's the logic underlying, what's a symbolic representation of events that underlies these neural nets that were developed by McCulloch and Pitts. So this is already some signs that people from early on were interested in seeing these fields integrated. So there are some people who do not like or do not appreciate that neural networks or machine learning are integrated with symbolic tools. They think that symbolic AI is gone and past, but I do not adhere to this community. I believe that both fashions of AI, or both communities, or both approaches, have a lot to offer to the field. AI has gone a long way. There have been several winters. AI winters is another term that's very well known in the community, but we are living in a reality now that even other fields, if we look at the Nobel Prizes for chemistry and physics, they recognize some of the efforts of AI researchers, and it's undoubtedly a great recognition, a great, let's say, scientific recognition that AI or AI techniques were bestowed with perhaps the most well-known scientific prize that there is, the Nobel Prize in Physics and Chemistry in 2024. So AI is being used across the board in science and technology. Other signs of the AI impact, or the impact of computer science, of course, the impact of the web in the 90s, the impact of AI, in my perception, at least in the research community, was again getting more attention after that famous series of of matches between IBM Deep Blue and Garry Kasparov in 1997. Garry Kasparov once famously said that he was the first knowledge worker displaced by technology. So he said that himself. And perhaps we are starting to see a paradigm shift, and some have already claimed that we've seen a paradigm shift given all the signs. But anyway, what's the relationship with neurosymbolic AI and this field of AI that's very vibrant? So already in 2017, so I bring this slide on purpose. This is 8 years ago. It's going to be like 10 years ago very soon. Scientists were already concerned with issues like interpretability, verification, validation of machine learning or AI systems, questions of fairness and dealing with real-world data in an efficient way, understanding causality, and offering and building systems that are safe and secure. So these questions have been here. They haven't received as much attention from the community. And maybe one of the reasons is that we haven't got the proper tools. And we believe that neurosymbolic AI tools, not only us as scientists and researchers and academics, but also industry is getting more and more involved in neurosymbolic AI. And other motivations for the field, from early on, other researchers have seen the need for a principal way of integrating machine learning and reasoning. Even Les Valiant, in some of his writings already more than 20 years ago, in a small piece that he wrote for the Journal of the ACM, a very well-known journal, very respectable journal, he said that one of the big challenges for computer science was to develop a way of integrating learning from experience and the ability to learn to reason from what has been learned in a sound way, in a way that we have a language, we have systems and languages that offer a way to describe algorithms that a neural network may be implementing. So we need the semantics for the process that is happening in AI these days. And the reality is, when we see some of these news, some of applications, we see that the models that we have today, no matter how good, how effective, how efficient they seem to be, there are fundamental questions that they cannot still handle, fundamental issues they cannot still handle. For instance, this piece in the MIT News showed that visual language models, they couldn't handle queries with negation, with negative words. And this is an issue that has a strong correspondence with research in logical AI, for instance, in logic programming and in other domains of logic-based and computational logic, where negation is a challenge to deal with in several implementations of logical reasoning. And now, okay, when people try to implement reasoning, and I quote reasoning here, in a naive way, in a large language model or in a visual model or in a multimodal large model, they will confront these problems that are by nature logical problems, computational logic problems that have not been solved yet, and they can cause a lot of problems. I cannot provide a wrong diagnosis because I have a knot in the middle of a query or in the middle of a diagnosis. So, in a way, not only scientists, but I will show later that practitioners and industry are very interested in neurosymbolic AI. And again, more arguments that favor neurosymbolic AI are arguments for creating more transparent, more explainable AI models that offer clear insights on how the model works. And insights are not only naive interpretations, but they should be formal interpretations. Even if we want, for instance, to build and to develop safety critical systems, if we want to develop autonomous machines like cars, airplanes, and you name it, we need to have self-explaining architectures that can anticipate failures, right? That can be self-verified so that the systems are indeed fault-tolerant, safety critical. So how this field has developed and how this need scientifically has been identified. The reality of AI research, and that's maybe why Alex mentioned that we have been pioneers here, is that in the early 2000s, when we look at AI conferences, even the field of neural networks was kind of, under the view, it was not very, very well seen at the time. If we look at the top conferences, early 2000s, in machine learning, people were developing so-called graphical models. They were developing support vector machines. They're developing Markov models and other Bayesian models, and you name it for machine learning. But neural networks were not seen anymore as a promising way. But in the mid 2000s, Jeff Hinton published a paper in Neurocomputation that was called a fast learning algorithm for deep belief nets. This is one of the modern uses of the adjective deep with neural networks. And there he showed that deep belief nets or networks with multiple layers could be very effective in image recognition, image processing, and so on. And after that paper and several other papers about that time, the community went back and started paying more attention to neural-based machine learning. And then, of course, there was an explosion of interest after the famous ImageNet challenge in 2012, where neural networks beat the other the techniques by miles. And then the rest is history, and we got to the point that we are today. But today, the challenge that we have is dealing with not only the logical problems that we see in those models, the inconsistencies that we see, but the practical problems that these models have, including hallucinations, including logical errors, including self-contradictions, including the cost that they have, the cost, the footprint that these models leave. And sometimes for very simple tasks, is it worth using such level of investment to solve a very simple task like people are doing these days? What's the cost of the queries, of the cost of training these models? So this kind of concern, this kind of approach is also under analysis, including by the very respectable AI Index report that Stanford University publishes every year. And they see here, we see an escalation of the cost of just training the models, right? So training the models has got extremely expensive, like in the region of hundreds of millions of dollars of investment. So much so that even academic research on large language models is becoming harder to perform in terms of developing new models. But here is another representation that you can see the estimated costs. But even more important than the costs is perhaps what the users of these models experience. And there was a survey research carried out by Centaur and Stanford University in 2025. And they identified what kind of AI-related incidents were reported by organizations using these models in the past 2 years. And you can see that adversarial attacks, privacy violations, unintended decision-making, model biases, performance failure, they're still in the region of around 50% or sometimes more than 50% of organizations experience these challenges, right? So, and the big challenge here is that we do not know exactly how to solve these issues because the interpretability question, because the explainability questions, they need better techniques, they need better science to explain how these things work, or we need even better science to have what I call a lighter AI, an AI that requires much less investment but delivers the same results. So another important thing when we are developing technologies, when we are thinking about science, you might remember that the Nobel Prize for the Nobel Memorial Prize for Economic Sciences in 2025 was awarded by researchers that studied technological innovation. And one key insight there that is relevant to the state of AI today is that technologies started being relevant in the economy when people started to understand why things worked. So technologies that people did not understand why they worked, where the science was not well understood in the development, they failed to generate the applications that made them useful in the production process. So in terms of investments that we do in these technologies, the investors can be wasting money or valuable resources in terms of putting money where we're developing things that we do not understand. And this quote in the Nobel Prize announcement, and was quoted by Professor Joshua Gans from the University of Toronto, who studies technological innovation. He has one of the leading groups in understanding the impact of technology in the business world. And it represents perhaps some of the things that are happening now. We do not understand properly how this AI works today. And we think that these AI technologies should be better understood, not only for the sake of science, but also for the sake of their deployment in business, their deployment in applications. So the history of economic science showed that technologies are widely deployed and they create value when they have the science underlying the technology very well explained and very well defined in terms of its principles. So, okay, in our case, how we integrate learning and reasoning, how we can build safe and reliable technologies. Another motivation that we see here is that how we integrate things that seem so disparate. But this is not a novelty. A lot of people now quote this book by Daniel Kahneman. And Daniel Kahneman, he used to say that unfortunately people only read the first 100 pages of his book. The best part of the book comes later, right? After the first 100 pages of his research. But the point here is that he developed this theory called dual process theory, where basically when we analyze the reasoning ability of humans, he was a cognitive scientist and economist, and his research in cognitive science were applied in economic science. He realized and he uncovered that we as humans have two kinds of systems or reasoning systems, or we display this kind of system one, system two difference, duality. The first one is, of course, people are well versed in this definitions these days, is that system one is intuitive, very fast. We recognize things and standards and patterns immediately. When we see something that scares us, we immediately react. We don't take 5 minutes to react to some threat. Right? The other system is system two. When I go to take a new test or an exam at school, where I need to have a very hard discussion with some member of the staff in our company, we're very reflexive. We think for hours about what we're going to say. So this kind of system is kind of performing logical reasoning, bringing new assumptions, and preparing you for a more challenging scenario that we have not been trained. And in Kahneman's words, in one of the debates, the many debates that he took on the future of AI, he said that so far he was concerned, system one certainly knows language, because we use language to represent certain kinds of actions that we have. And system two does involve manipulation of symbols. So this is also a motivation, and the motivation to use AI. The field has evolved and to use, not AI, pardon me, to use symbolic techniques or computational logic techniques aligned and in a compatible way, or fully integrated, or loosely coupled, or more strongly coupled with machine learning techniques. This led to several debates to understand how these things could be integrated, including the summer schools and the workshops that Alex Gray himself has organized, the summer schools and Centaur AI Institute that dedicates itself to the future of AI and to the future of neurosymbolic AI research. But now what we have seen as well is that companies are defining their systems or calling the system or seeing value in using neurosymbolic techniques, and companies like Google DeepMind and Amazon AWS are using such techniques. So from a technical point of view, these things started by realizing the connection between system one, system two, and neurosymbolic AI, where we could see the connections between system one being the machine learning system that recognize patterns very quickly, and the reasoning system, system two, being represented by symbolic techniques, computational logic techniques. Another point that people also cite frequently in papers is the so-called taxonomy, or the taxonomy that Henry Kaltz defined in his address at AAAI 2020. He later published a refined version of this paper in the AI magazine. And this also helped to start organizing the field, how neurosymbolic AI, a taxonomy, could provide an initial organization of the field, so that when people develop their system, they could say, well, am I doing neurosymbolic AI or no? How can I guide my development of my research, of my new technology, of my new system, so that it adopts certain AI technologies? So this division and this technology this taxonomy is relevant in the sense that science has to be an organized effort, and technology has to be even more organized. And if in the future we are going to have an engineering of neurosymbolic AI, we need even more organization to have the methodologies very well placed. And this division, I hope that it ends. But recently, or over history, AI has been divided. I already mentioned it, but just to reinforce my point, the symbolic and the connectionist schools of AI, or the computational logic community and the machine learning community, both have brought several important and relevant contributions to the development of AI. The first AI researchers, including Simon and Newell, they were symbolists. They developed several applications like theorem provers. They're trying to solve chess in 10 years to defeat a human being in the 60s. Of course, they were not able to do it. It happened in the 90s. And then we had a lot of developments in neural networks by as a community represented here by three names that received the Turing Award in 2018. But we also have had people like Les Valiant and Jude Pearl. Jude Pearl is very famous for developing models of causality and the application of Bayesian techniques in artificial intelligence computer science. These researchers believe that an integrated learning and reasoning sound AI is the way forward. But what is Neuro-Symbolic AI? And now I'm going to bring some technical results for those who are eager to technical results and to technical approaches. So Neuro-Symbolic AI, in our view, in our perspective, or even in my perspective, is to develop systems, technology, and science where we can learn from experience, from data that we collect from an environment. You can think of this environment as a robot moving around a certain place, or you can think the environment as collecting visual information about something that is relevant in the domain of autonomous cars, or any other information that you can see or knowledge that you think is relevant for your application. But more important than gathering this knowledge is to reason about what has been learned in an uncertain environment in a computationally efficient way, providing a semantic. So in my perspective, Neuro-Symbolic AI helps to solve or helps to understand questions related to, for instance, the behavior of models. Why did the language model do this thing that he or she or it represented, right? So these models, some people think that they have personalities, they have gender, they are he or she or they or it. But why, to me, the question is, why did the model do it? So is the model logically consistent? So is the model always answering the question in the same way? We have already experienced, all of us can experience when we do, and we still twinkle the questions in different ways, or we do some questions that perhaps are similar. Sometimes the models hallucinates. And even more important, if we're dealing with applications, can we verify these systems? Can we, for instance, verify the safety of these systems? Can we verify the correctness, the soundness of these systems if we are deploying them and millions of people are using potentially? So, and I draw an analogy, of course, between neurosymbolic systems and learning systems with the process that children used to learn. This picture is of my daughter when she was very, very young. And one day she gathered information from her experience, of course, with us. We used to brush her teeth when she was very young. And then she learned from experience that she could do the same with her dolls, right? So here is a human agent learning about how to repeat patterns, how to learn new things and reason about the data that she observed from the world. And they use different techniques to reason. They use abduction, they use deduction, induction, and other probabilistic reasoning techniques, of course. So there is indeed a motivation to bring systems where I will learn from the environment, and learning from the environment. And our point early on is that classical logic, or the logic that represents predicates, that represents static information that is used in mathematical logic, is not the logic that's necessarily the best logic to represent neurosymbolic systems or to build neurosymbolic AI systems. But this is also a novelty because there is a large community in computational logic, in artificial intelligence, that has developed the so-called temporal logics to deal with space, time, to deal with uncertainty, to deal with common sense reasoning, to deal with common sense knowledge. And they uncover and they discover that classical logics, or the logics for all existent predicates, is not always the best logic to represent what's going on in computational applications. The notion of time is crucial in the logic that we use in computer science, but the logic that we use in mathematics, typically time is not a variable. When someone is proving a theorem, someone is not proving a theorem in pure mathematics or applied maths, considering the temporal variable. in general. But in computer science, as we are executing and running programs, the temporal dimension is key for any system that we develop. So this remits us, and this asks us to use this kind of non-classical logics. And if you are interested in non-classical logics, those logics that go beyond the typical axiomatizations that we use in mathematical logic are logics that have been developed mostly in computer science. Computer science has been the key engine of logic research over the last 60, 70 years. And the computer science literature is rich in terms of developing these systems that are based on these novel logical systems that were mostly developed over the last 50 to 60 years. There is some classical literature on how to represent the interaction of multiple agents, the interaction of distributed systems that have been developed by a number of researchers, and those literatures have very high quality. So again, these are the questions. I'm going to now use a very simple system because I wanted to present a system where there is a full integration of logic and machine learning, or logic and neural networks, right? I'm going to show a system where the logical representation, or the representation of the rules of the systems, or the inference system of the inference rules, happens inside the neural network. There are different ways of implementing neurosymbolic systems. I'm going to go back to the taxonomy, but first I'm going to give you one of the first systems that, or considering the age that these publications have, like from 20 years ago, a system that we have a full integration of machine learning or neural learning and logical system. And again, those are questions that we are trying to answer. What the model is going to do? Is it logically consistent? And can we verify certain properties? Some of these questions are the questions that, for my research, I think are relevant. So where we draw inspiration. So some people might get surprised, but already in the 90s, people were trying to represent logic programs within neural networks. Why this research started? There are several reasons to justify why this research started. Some people say that in the fifth generation project, the Japanese fifth generation project, people were interested in building parallel machines. And people thought that perhaps neural networks could be a model of parallel computation of prologue programs, because Prolog was one of the key languages used in the fifth generation project, financed by the Japanese government, Fujitsu, with a lot of involvement from Japan. So people started developing ways of representing logical problems and logical programs within neural networks. So the idea was to build algorithms that translated logical problems into the structure of neural networks, not to use them as separated entities. And already in the 90s and the early 2000s, several researchers like Jude Chavlit, Arthur Garces, Gerson, Zavarusha, Stefan Hodobler, the late Stefan Hodobler, they developed several results on how to represent properties of fragments of prologue problems. And in the end, what was a very interesting result was that this result from the late 90s, that any logic program can be represented in a neural network that is going to be capable of computing the program, the result, or the fixed point of the program. So this was a very interesting result because it opened several ways of analyzing how neural networks could implement inference rules. If they could implement in principle inference rules in Prolog, why couldn't they implement other logical mechanisms, other logical systems? And our choice of language, our choice of logical language at the time was, okay, if we want to represent agents interacting in an intelligent system, if we want to represent multi-agent systems, and multi-agent systems at the time were a hot topic of research in AI. Now multi-agent are back into the fore, and everyone has rediscovered that agent systems exist again in technology, but multi-agent system or agent AI has a long history in AI, of course, that we have to consider. So our idea was, okay, how we represent modal logics, and modal logics are very good to study because the modalities can represent temporal dimensions, they can represent beliefs, they can represent probabilities, they can represent uncertainties. So if we uncover a way of representing modal logics or inference rules of modal logic in neural networks, that would open several possibilities for us to understand how neural networks learn and reason over different logical systems. And then we can, in principle, tackle different problems that have to be solved in computer science. So the idea of modal logic is simple. We extend classical logic with modalities, thus the name modal logic. And typically those modalities, like in classical logic, we have a modality that represents concepts of universality, and we have a modality that represents concepts of existence, of possibility of certain propositions being true in a possible world. And possible world is a very interesting model of semantics. It was developed by Saul Kripke still when he was a teenager. When he was 18 years old, he published his famous paper on the semantics of modal logics. Actually, he published more than one paper. And the semantics and the possible world semantics turn out to be extremely effective in computer science because there is a relation between state machines and possible world semantics. So in our systems, what we see is that our insight is that we assume that the neurons or ensembles of neurons or subsets of neurons could be seen as possible worlds. And propositional modal logic is a decidable fragment of first-order logic with two variables. So we have here a relationship, an interesting technical relationship between modal logics and first-order logic. So in a limited sense, in a limited scenario, we can represent relationships between agent and objects. So we are able to provide, using the system, a full solution to some classical problems like the Muddy-Trudon puzzle, Weismann puzzle, several puzzles and test beds that are studied in the domain of distributed logics, in the domain of logics for multi-agent systems. And we are capable of producing some technical results where we could compute, we could teach, or the neural network could learn to compute the result of certain modal logic programs and reach the fixed point of the program, right? So we are capable to produce a formal result. And what we did was to take the inference rules for modalities, and those are example of modality rules of inference in a system, in a labeled system of natural deduction. In natural deduction, we have rules for elimination and introduction of the connectives that appear in the formulas. And if you want to represent, say, a program P, like this one here in the bottom line, where we have three possible worlds in this program, or three states. If you are a computer scientist, you've never seen possible worlds, you can interpret the possible worlds as states of a program. Say in state W1, we have certain propositions that are valid, certain variables that have a certain value in a computing system. In state 2, we have another proposition that's valid. In state 3, you have other things that happen in the systems. And we showed that these rules could be represented in a neural network, and you could even build a pictorial representation of this neural network. But in order to represent those inference rules here that we're seeing here in this slide, for instance, to represent how we can eliminate a diamond in modal reasoning, how we can introduce the box in that's the universal modality in modal logic, we can translate these rules into a neural network using a translation algorithm. So if you go and check in our book or in our papers how to represent inside the structure of the neural network, so in our way, we are not connecting the neural mechanism with an external theorem prover. And one of the applications that is very successful these days is the integration that AWS did of generative AI models with external theorem provers like Lean to verify properties of these systems. What we did was not that. What we did was a fully coupled neurosymbolic approach. We translated the machine inference rules or the logical inference rules into the structure of the neural networks. We reconnected the way that the layers are built. We reconnect the way that you connect the neurons, so that when we receive and when the neural network sees as input some logical inference, the inference is executed, is run by the neural network. That's why I call this system a system that is a system that is not recent, but is a system that is fully coupled. And I think that we are going to have purely or fully integrated neurosymbolic AI on the day that when we have machine learning, where the learning mechanism is fully integrated and it's not externally representation. They are not coupled systems where one component does all the neural part or the learning part of the AI system, and the other symbolic component, logic component, does all the logical inference, right? So we have theory improvers that have been developed in AI, like Lean, I already mentioned, is an extremely successful tool. But Lean is not a neural mechanism. The inferences in Rule, they are not derived by a neural network. They are derived by symbolic mechanisms. This is a neurosymbolic system, but it's different from the perspective that I'm presenting here. So in the end, we're capable of showing that for any model, and we can say for any temporal logic program that we define the language in the papers and we run some experiments, I'm going to show you next. There is an ensemble of neural networks, and we use multi-layer perceptrons with certain changes in the architecture that computes the result of program P. This is a theoretical result. And another point that's quite relevant here is that adding a temporal dimension is crucial here in numerous applications. So we have to consider how time evolves in the application. So the notion of time, the notion of representation of time is key in computer science. And we have, of course, to represent how agents interact and how they change their perception of the world given new information, right? So this is also very important. Okay, let's think now about applications of this. So I gave one example of one neurosymbolic system. That's a system that we call Connectionist modal logic. And I gave that example because that system is a fully coupled system. There are other ways of developing neurosymbolic AI systems. But the key question is there any application for this thing of computing logical inference using neural networks? So already in about more than 10 years ago, we showed in a number of experiments that we could, of course, in principle, use these applications in software engineering. And I'm very happy that these days, this principle is being used across several papers and applications in software engineering. If you go to the main conferences in software engineering, like the ASE or ICSE or FSE, you see people using exactly the same principle, but not exactly in the same way that the technically implemented. Basically, what we did here, we coupled a neurosymbolic mechanism with a model checker, and we used the model checker, we used the counterexamples produced by the model checker to refine the initial model of the system that we had. So in this way, the information that was provided by the model checker, symbolic information, was used as input to a new run of the system where an external, a coupled neural network or a learning engine would refine the model until we're satisfied with the level of correctness that we define. So this idea has been developed later on. So the counterexamples are used as input of the adaptation engine or the learning engine in order to obtain new improved models. And you can think in terms of model refinement in software engineering or requirements, specification refinements, and so on in terms of applications. And as I mentioned, there are other ways of applying neurosymbolic AI. The fully coupled or the strongly coupled approach that I called Connectionist modal logic is not the only way of doing it. Even the Wall Street Journal has recognized that neurosymbolic AI exists, and Amazon is doing neurosymbolic AI. If you go to Amazon Science pages, or even if you go to their very well-known event last week, I think happened, reInvent, there was a talk or more than one talk mentioning the use of neurosymbolic AI. So what Amazon is doing here, what Amazon is benefiting from, and Byron Cook, who is vice president at the AWS and is a well-known researcher in the theorem-proven formal methods community, he said that there is a rise of interest in neurosymbolic AI because people are realizing how important the work in theorem proving, how important the work of integrating those systems to produce, of course, safer AI, more reliable AI for a company that has perhaps millions or certainly hundreds of millions of customers and has to interact with them every day with a degree of certainty of more than 99%, right? So Amazon is using neurosymbolic AI to minimize AI hallucinations, to, as I mentioned, to deliver 99% accuracy. And they are combining here with some certain tools. And one of the tools is the Lean Theorem Prover. And Amazon is mitigating hallucinations. And they are using the so-called neurosymbolic AI guardrails using Lean to check and validate the AI outputs. Because when you are using a generative AI output, they have this the suite of models called Amazon Bedrock, and they have now guardrails that allows the systems to self-verify if the rules of the system are being followed. For instance, if I'm not selling things to the wrong person, if I'm not giving too much credit to someone. So in the finance domain, you see more and more, not only at Amazon, I know of other cases using the financial industry, where you have to verify very strict rules of course, lending money to people, giving credit to people, and those rules and those outputs of the system, they cannot have the level of uncertainty or hallucinations that are created or generated by large language models or other generative AI models. So just to strengthen the case, of course, I already presented you the arguments of why Neuro-Symbolic AI is relevant in the domain of language models, especially in applications and combination of theorem provers and formal methods at certain companies with large language models. But there are other models in the scientific domain from other companies, like the alpha family of models, alpha geometry. Some people can even claim that even AlphaFold is a neurosymbolic model because they use some probabilistic models combined with the neural learning mechanisms. So alpha geometry is clearly a neurosymbolic system. Everything that's in this slide, even the quotes, are from Google DeepMind. They are not mine. So Google DeepMind is stating that alpha geometry is a neurosymbolic system made up of a neural language model and a symbolic deduction engine that work together to find complex proofs of geometry theorems in this case here. Again, they also stated that the idea is akin to thinking fast and slow. Remember one of the first slides that I mentioned, dual process theory. And alpha geometry outputs, they are impressive because they are verifiable and clean. And basically, what we have is, if we want to prove a theorem in alpha geometry, I am coupled with a specialized model that can provide me extra premises, extra information that can be used by a symbolic prover, a symbolic theorem prover, or a symbolic engine. And by adding this additional information, combining the information that was added by the language model, say, or a specialized model that knows geometry, I can have a better way of proving certain theorems and relevant results in maths. So even Terence Tao, that's one of the leading mathematicians in the world, he's using these neurosymbolic techniques to implement and produce more and verifying if AI can help in producing significant results in mathematics. So basically, there is this buzz about solving Olympiad geometry problems, winning the computer science, the physics, or the chemistry, or any Olympiad that high school or even college students take part. And these papers have been published in Nature, and it's clear that the symbolic deduction engine or the neurosymbolic AI techniques can add to the neural techniques that are used these days and provide better results in neurosymbolic AI. Okay, moving next to the taxonomy, as I mentioned before, how neural networks, how neural systems and symbolic systems interact. It's well known that Henry Kautz, as I mentioned before, developed this taxonomy. And what kind of systems? When I'm developing an AI system, I question myself, am I doing neurosymbolic AI or not? So the taxonomy that Henry developed was very flexible. He considers that several systems that are already developed, have been developed, and will be developed in AI can be classified as neurosymbolic systems. So this first category, for instance, includes the standard deep learning. He claims that this is a stretch, and we recognize it's a stretch because he claims that, okay, I can include this category because any input from a neural network can be made out of symbols. When I do language translation, right, the languages, even if I'm putting the language to be translated by a purely neural system, the language is symbolic, right? Nobody uses a neural language when we are speaking or when we are writing. The other categories are systems like AlphaGo that I already illustrated, where there is a coupling of systems but the systems are separate. They are not like the system of connectionist modal logic that I presented. There are other ways of integrating neurosymbolic systems. For instance, this type 3 is, as an example, we have the Neurosymbolic Concept Learner. It was a system developed about 5 or 6 years ago by a group of researchers from MIT, where the neural network focuses in one task, like object detection, and interacts via input-output with a symbolic system that then labels and interprets the image or interprets the task, like organizing objects in a given domain. There are other applications where the symbolic knowledge is compiled into the training set, right? There is a compilation in an adequate way of representing this knowledge for a neural network to process. This was the approach used by Lempo and Charlton in a famous paper on deep learning for symbolic maths, where they showed how several results could be interpreted, how symbolic maths could be carried out in neural networks. And also, it's the case of Problog, that's a well-known language, probabilistic logic, that's developed by a group of Neuro-Symbolic AI researchers in Belgium and in Europe. Finally, the type 5 Neuro-Symbolic system is a system where the symbolic logic rule is mapped into a distributed representation, into an embedding, and it acts as a soft constraint on the network on the loss function, right? The loss function is a key aspect here. Certain systems that have been recently developed focus on this approach, and one of the examples of these systems is logic tensor networks, the system that there is an implementation, a prototype where you can run your own experiments. And finally, the type 6 system is what's called the true symbolic reasoning inside a neural engine. This should be a fully integrated system. So in our interpretation, in my particular interpretation, and that's the reason why I presented the Connectionist modal logic system as an example of fully integrated system, the neural network not only would be the learning engine, but at the same time, the learning engine would also serve, like the neural network would also serve as the reasoning mechanism. So the inference rules, for instance, if you take the inference carried out by Lin, that inference would be carried out inside, let's say, the neural network by the learning engine. So this would have like a fully integrated neurosymbolic AI system, right? And perhaps when we have that, we have a very effective way of representing neurosymbolic AI system. So what kind of tools are available to build neurosymbolic AI these days? So unfortunately, I'm running out of time, but there are 3 systems that I want to highlight here. One of them is logic tensor networks. Because I'm highlighting the systems because you can find implementations of the systems that are either very easy to use, like Python package, or product-like dialects like deep Problog. And for instance, logic tensor networks, as the name already says, it combines first-order logic, where the formulas are real-valued tensors, and the truth values are in an interval 0 and 1. So they use a tensorization of logical objects. They do a translation into tensor networks, and you have a degree of certainty if something is true or false. So I unfortunately cannot describe in detail because I want to mention other work that I think it's a very beautiful work on logical neural networks. And in this work developed by Ryan Riegel, developed by Alex, by Gray, developed by Ron Fagan, a group of researchers, they consider that every neuron would have a meaning, and every neuron would be a component of a formula in a weighted real-valued logic. Again, a real-valued logic, right, in an interval 0, 1. And the neurons can represent logical gates. And the difference here is that I can have inference that I called bottom-up and top-down inference, or I can have bidirectional inference in this kind of approach that they developed. Is again a very interesting approach. You can find their papers and some prototype implementations, and it's also a promising approach to represent relations that are key in computer science applications. And finally, another system that is under development. Perhaps this is the most well-developed tool that we have these days. I'm not pretty sure, but I know that Robin Manhiv keeps developing probabilistic logic programming. And the idea here is to combine the school of inductive logic programming, now called probabilistic logic programming, because they are combining the system of probabilistic logic programming with neural networks, where the neural networks represent neural predicates within the program. So the neural networks will present some probabilistic facts. They can represent the weights learned by backpropagation, then they can represent visual information like the MNIST data set, and you combine that with symbolic representations represented by the predicates of inductive logic programming. All these systems that have different bottlenecks. One of the bottlenecks here is the scalability, because we require a logic programming inference when the symbolic part is very complex, and the model design can be less flexible when we are thinking in terms of outside the logic programming paradigm. This is another thing that we still have to solve, and perhaps we need to develop systems where we're more fully integrated with the existing machine learning packages like TensorFlow, PyTorch, you name it, the ones that are coming forward, right? So in conclusion, what did I want to tell you today? In my perception, in my experience, in my observation of the community, Neuro-Symbolic AI represents a paradigm shift. And this is a kind of a bit strong statement, because I don't think scale was ever all that we needed in science. You know, science and technology have always shown that scale never solved all problems that we had in human life, right? Even if you think in terms of applications that we see today, we never use all the resources that we have available to solve a simple problem. Sometimes we take the Occam razor, and Occam razor tells you, oh, the best possible solution. We should take the most simple solution, but not the simplest one. So there are some certain doubts about the scalability hypothesis, or the assumption that using more and more data and more energy and more resources will solve all the problems or will lead to artificial general intelligence. I believe that this paradigm can offer this paradigm of Neuro-Symbolic AI can offer very strong contributions to the current state of AI, because we offer sound techniques for reasoning. The reason that we have in current AI tools, especially current AI, generative AI tools, it's not sound. Everyone can prove today by some simple queries in language models that the reasoning is not sound. We need a solution to explainability if those systems are to be robust in applications. The examples that I gave from industry here, they are seeking explainability and robustness using exactly symbolic techniques. We need a foundation for systems that we can trust. If we lose trust in AI, we're going to have another AI winter. If people start to think that AI is not delivering the results that they want, trust is key in business and in economics. The economy that we have today is based strongly on trust as well. And I believe that the Neuro-Symbolic AI can be the third way for AI to build systems that are intelligent, they are interpretable, they are data efficient. We can even process information out of the distribution for those that are data-centric researchers. And more important, they are safe to use. Bringing more subsidized to conclude, building broader, building safe AI technologies. There are several alternatives. My approach, or the approaches that I presented here, are not the only approaches that exist. Sepp Hochreiter, who is a well-known name in machine learning, he developed of course, LSTMs. He saw a couple of years ago that in his perception, the most promising approach to broader AI is also Neuro-Symbolic AI. And he advised in this piece, in this paper, that graph neural networks could be one of the predominant models of Neuro-Symbolic computing. And we've wrote about the applications of graph neural networks in Neuro-Symbolic AI. If you want to have a look and discuss the ideas that can be deployed, this is also an interesting approach. Finally, some technical challenges that are still open. When Arthur and I wrote that paper, we highlighted a few challenges. These challenges are still open. If you want to understand higher order knowledge extraction from very large networks, and if you want to show that the knowledge extraction and the representation of this knowledge is sound and efficient, this is still an open problem, and this is where Neuro-Symbolic can contribute. If you want to have common sense efficiently in large language models, we still do not have perfect common sense. We still have hallucinations. If I have hallucinations, it's clear that I'm talking, and I quote talking, to a language model that does not understand common sense. If it's hallucinating about some simple subject matters that I'm discussing with it, it does not understand fully the context. Also, human network communication, as we called at the time, as part of a multi-agent system, is also a relevant problem today. Today, people are referring to agents being pre-programmed or vi-programmed, or with the code generated. But how these agents communicate in a way or argue in a way that they respect security and safety protocols with the user, they can ask questions and they can check and validate their understanding. Another open challenge that I think is a foundational open challenge, you can realize by my interest that I'm interested in the fundamental points in Neuro-Symbolic AI. I like the technological applications, but I'm interested in fundamental questions. Axiomatizing Neuro-Symbolic AI, right? There is an interest. When you want to organize a field, you have to define what are the principles of this field. Everyone knows in physics what are the principles of classical mechanics defined by Newton. Everyone knows what are the principles of electricity and magnetism defined by Maxwell, and so on. But what are the principles of Neuro-Symbolic AI? What are the axioms of Neuro-Symbolic AI? The truths that will hold for any system that combines neural networks and symbolic techniques. So building a consensus around these foundational principles, to me, it's a challenge. In the unified, you can offer a unified foundation to reduce the overhead of describing new systems, facilitate collaboration across subfields, foster clear communication in the area, avoid also fragmentation, redundancy. And there is an interesting paper published at NESI 2025 that also tackles this approach, a paper by Pryor and Guitor on neurosymbolic architecture and axioms for integration. And also in our book, already in 2009, we're trying to work to axiomatize logics that represent neurosystems. And finally, if we want to raise awareness, we have to work on neurosymbolic AI education, how to design robust tools for a semester-long course, and more. And I provided recently a first version of what I think could be taught over a semester in neurosymbolic AI. Okay, this is how the field can contribute, how the field can help to develop better technologies. And I hope this overview can provide you some interest in the field. I provide you some references here, some papers on the work that I mentioned, a paper on logical neural networks published in the PNAS, and also in archive, a paper on DeepRoblog, a paper on logic tensor networks, some survey papers, some collections of papers, editions that we have organized, the community has published over the years, and also some books that have been published. Pascal Hitzler has recently edited 3 volumes in addition to what exists in the literature. Thank you. I have to stop. I know that I might have run a little bit over time, but I thank you again for the invitation and everyone for being here. Okay. Thank you.
Okay, thanks so much, Luis. Yeah, so you heard it from one of the original sources, although, as Luis himself said, there's an argument that Neurosymbolic goes all the way back to 1943. But still, I would say when people ask about the history of Neurosymbolic AI, of course, we have to go back. I think we have to look to the sort of end of the dominance of symbolic AI, roughly maybe early 90s. And then Neurosymbolic AI sort of, you could say, was a counter reaction a little bit, or at least, hey, we've got these 2 paradigms. Let's, they're kind of complementary and opposing, it seems, but maybe we should combine them. So it wasn't until the 90s and early 2000s that you could say it really started.
Yes.
And enter Luis and collaborators. So a few things. So I just want to point out a lot of the luminaries that and key figures that Luis mentioned, we've had essentially all of them in our series over the last 4 years. And in case you're confused, that was also us, the IBM time period when we were doing this from IBM. Now we're doing it from the Institute, this series of summer schools and events. That Neurosymbolic program goes back to 2018 at IBM. But yeah, we had Gary Marcus a few times, Henry Kotz, Arthur Garces, Les Valiant, Yuta Pearl, Ron Fagan, and Moshe Vardy, among key figures that Luis mentioned. I think maybe I was reviewing Pascal Hitzler and Lise Couture are some of the few we haven't had yet. They're, I think, very important leading important groups. Now, also Yasha Benjo representing, let's say just adjacent to Neurosymbolic. Yes. So, Luis, you mentioned modal logic. Oh, first, I think that there's a question, Olga.
Yes, I do have a couple of questions.
Yes.
Was there anything from the audience?
Oh, from the audience, there was one question. It disappeared though.
Oh, it disappeared. Okay.
Yeah. I think it was about this connectionist modal temporal logic system.
Mm-hmm.
Oh, okay, I see it. In this work, does observed data backpropagate into the logical neurons?
Oh, yes. You can refine the learning procedure. Yes, it does. We use backpropagation as learning. It's standard backpropagation. Even the first approaches, you remember when we started doing this, we didn't have the GPUs we have today, so we have to be very effective. So we used standard, the most efficient available backprop implementation that there was. Yes.
Very good. So, in reviewing the different kinds of Henry Kotz's taxonomy, I think, as you mentioned, there are approaches that are strictly separate neural and symbolic systems that are coupled somehow in various ways. Most of the categories are like that. And then they're all interesting in our view, and all provide some interesting value. So, and then the sixth I want to get to is maybe the most integrated.
Yeah.
I want to dive a little bit more into just how integrated. But just to mention, there are pros and cons to whether you're completely decoupled or fully coupled.
Mm-hmm.
It's been argued by some, for example, Francesca Rossi has a really interesting system. Is literally a system 1, system 2 kind of implementation, and you have a sort of a metacognition process overarching the two systems. And they argue that, and I think it's a valid point, that actually there's a great advantage to keeping them completely decoupled, because then, the state of the art changes in each side. You get a new neural net, boom, just plug it in. And you get a new planner or theorem prover, boom, just plug it into the system 2 side. So, what would you say are the pros of the fully coupled side, or anything in between?
Yeah, I think the fully coupled side first is more challenging to build, because if you think a neural network that will do learning and reasoning in its architecture, it's going to be more complex and so far more inefficient than keeping some decoupling. From a technological standpoint, what you said makes sense. As you said, as the state-of-the-art advances in symbolic AI or advances in neural networks, you adopt or you compose compositionality with the new techniques and new system. This is an advantage from a technological point of view, I think. From a scientific point of view, I'm very curious about how to build this system that is fully integrated, that it's so fully integrated that we wouldn't call it a neural network or a theorem prover. We would call a different thing. So far we call it type 6, right? So when you develop a special architecture that performs the logical inference, and the learning purpose of this architecture is to learn the logical inference, then the full architecture is going to dedicate itself to learn whenever I see, for all x, p of x, then p of a, that will going to be happening inside the neural network, and the inference rule, let's say, for those that are more technical, or quantifier elimination is performed by the neural network, by nothing outside the neural network. Of course, this makes things more challenging because the way you develop the foundations of neural networks, say, lie in continuous maths, and the foundation of computational logic they lie in discrete structures and logical structures that are not easy to integrate. That's why when you did your work on logical neural network, you also used different approaches, not purely symbolic. You had to consider real values, real valued logic, and so on, to develop a proper correspondence between logic and neural networks. Yeah. So I think there is value in what they said. I'm not saying I'm right. What I'm saying is very challenging to do the type 6.
Very good. Well, do you remember the example that Henry gave for type 6?
He said there wasn't a clear example. No, he didn't give an example. He said that this would be a fully integrated system where the reasoning happens inside the network. So I claim that this connectionist modal logic is one of the systems that is probably the closest thing we have to live to level 6, to type 6. Yeah.
Yeah, there are very few examples. So it is kind of one of the big challenge areas of Neurosymbolic.
Yes.
Olga, did you have a question?
Yeah. Actually, we received a couple more questions from the audience, but I do have a question on this topic, so I want to ask it first. Actually, had a question about what type is this system, but I think Luis just mentioned it's probably closest to type 6. Another question that I have, could you please provide an example of what this system can do or solve, and how it compares to standard neural net, trying to feel these benefits of this neurosymbolic architecture?
Yeah. So in this case, if you don't have a way of representing, say, in terms of prologue-like programs or prologue-like clauses, or symbolic information in an effective way, translate it to what we did via this algorithm to have the inference rules, you cannot execute, let's say, the inference in the way that you have logical inference rules that are represented in the original logical system. So say we take the rules that I showed briefly in a slide. What we did was we took the rules of natural deduction in a finite universe. This is very important, in a finite universe. So it was an approximation of natural deduction. And we showed in this finite universe, but constructible universe, you can build this universe as big as your computer can support. We showed that if you have logical representation, or let's say, call it a modal logic program, a prologue program with modal predicates, I can use this as input, and I have the inference that the program, a corresponding prologue program, like the resolution-based prologue, would compute in the neural network. But if I don't have this proper representation, right? Just by exposing the neural network to prologue clauses, and I don't have any representation of the inference rule, it will never reach the result of the inference that the prologue program does, because I'm not teaching the network the logical inference rule. So the key thing here is to teach the network how to do the logical inference rules of a system, right? So this is the key thing that a neural network will not do by itself. If I take a standard multi-layer perceptron, recurrent neural network, whatever, it's very hard to just by looking at data to understand how inference works in the systems. So that's why I think this system is interesting to do. Of course, you have other systems like the ones I mentioned, logical neural networks, they use a different approach. But the way that they do, they have a correspondence between the neurons, between the formulas, and a weighted real value logic. There is a correspondence, but they do not have, let's say, the same way that we implemented inside the neural the inference rule. That's not how they do, right? Or logic tensor networks. I think this is the system where the inference rule is learned by the neural network. One of the things that you have to think that should be better managed, okay, but how do I have, let's say, a theorem prover with this system? I would have to coordinate what kind of information is run by what kind of network that performs certain inference rules, different inference rules for different operators. The same way when I'm building a proof and I see box alpha and diamond whatever, I know, oh, here I have to use AND elimination, or then I have to use box elimination, then I have to use diamond elimination. How do I teach the network to follow this sequence of operations in a proof? So this is the difference. If you don't have this defined in the system that we define, it's going to take a lot of effort to represent in a structured way how to make logical inference. I think that's the key advantage. And by doing that, we are capable of solving the same test beds that the authors that Alex mentioned in Reasoning About Knowledge had, like Wiseman puzzle, Monty Hall puzzle, all those puzzles used in distributed agents. We're capable of teaching how the network could reason about those problems and solve these problems. Yeah.
Okay.
Other questions?
Yeah, we got a couple of questions from the audience on Discord. An interesting question. So, in one of the earliest summer schools, Gary Marcus once called Kahneman being just a reframing of Freud. I think he meant Kahneman System 1 and System 2 being a mirror of Freud's id and super ego, just removing Freud's ego as a mediator between those two. Wondering what your take on that criticism is.
Oh my God. Well, I'm not a psychologist. I'm very naive in psychology, I would say. But if Gary, who is a cognitive psychologist, said that, I think it's a relevant comment. So I would follow those who know more about psychology than I do. And if in fact it's a reframe, it's an interesting reframe, because if you think in the future, people want to build AGI, right? So if you want to build id, ego, and super ego in the future, if you believe in this theory of Freud, then you are going to use neurosymbolic techniques. So this is an interesting way of seeing it. But we have to analyze the ethical issues, the medical issues, the social issues, all these consequences if you are building a system that mirrors id, ego, superego, and other Freudian theories. Yeah, that can be dangerous.
I'm also not a psychologist, but if the id is a mediator, then it does sort of seem to match the metacognition framework of Rossi et al.
Yeah, but that's a very interesting observation, because the connection between psychology, cognitive science, philosophy, and AI is deeper than many people outside the field notice.
Okay, thank you. Another question. When talking about building an integrative system, do you think that cognitive architectures could fulfill this role? For example, ACT-R. I'm not sure I know all these systems and pronounce it correctly, but it's ACT-R, Clarion, SOAR, etc.
Yeah, I know. Yeah.
There have been efforts to extend some of these with neural networks. If not,
Yes.
what are they lacking?
No. They are very interesting efforts. They are, I think, they are very related. This work by Paul Smolensky. He's also a cognitive scientist. He developed several cognitive architectures. He used tensorial approaches way before TensorFlow, way before that, right? If you look at Paul Smolensky work already in the 80s, he was using tensor models for cognition, right? So, and he's a cognitive scientist. So there is a lot of benefit that we can borrow from the cognitive models. Yes, absolutely. Maybe they can even provide a better explanation for what we are doing in AI. And sometimes we don't have the nomenclature, we don't have the taxonomy, we don't have even the understanding of what's going on. But we can draw from cognitive science and cognitive architectures the concepts that we are developing and using. Yeah, that's a very good, very strong point, I think.
Yeah, actually, SOAR and ACT-R, these kind of these architectures were actually extremely influential, and sort of arguably went closer to the prize of AGI than many other kinds of systems. They really were trying to be more general. So I think if anyone wants to put a link to some of these approaches that were mentioned where they integrated neural or other learning systems, maybe we could invite them. I think that would be very interesting to look at.
For sure. This is highly relevant. Yeah, for sure. We even have had cognitive scientists not only in the summer school, but in the NASI conferences as well. So even their research papers are welcome in the community. Yeah.
Okay, thank you. Now a question from LinkedIn. How to quantify or impose a failure tolerance threshold for a type 6? Is it not generalizable since it is domain dependent by nature?
Well, that's why it's relevant to have an axiomatization and then to define the principles of the field. Then you can start developing better metrics as well. It's kind of domain dependent. You can think of it, but for instance, if my objective in the type 6 is to develop something akin to a theorem prover, right? A theorem prover that learns the inferences by itself, right? I can use the same metrics that I use in theorem prover, correctness or soundness and so on, right? The logical metrics for theorem provers, right? This can be a metric that we can use, right? Or we can compare with the results that theorem provers have in the same kind of task, right? And then this comparison, we have benchmarks and we see where we are, and this can define the metrics that we're going to go. So accuracy is clearly, in logic, accuracy is a clear metric, of course, just to illustrate the point.
Others from the audience? Olga?
Yes. We have one more question from Discord. How do you envision training working in a neurosymbolic system? I think one of the reasons for the popularity of generative AI, both success and failures, is that it can ingest all kinds of information, some of which is undoubtedly contradictory. It would seem that to get sound logical answers from a neurosymbolic system, some of these contradictions would need to be definitely resolved. No?
Yes, but I mean, the contradictions stem out of the Gen AI, if I understood the question, right? So there is another thing that logic offers is a way of handling contradictions. This is well known in logic. You have these paraconsistent systems where you learn how to prioritize what you solve, right? So you can tolerate contradictions, you can tolerate inconsistency, and there are ways of integrating that into the current state of language models. Okay, so if the question is about how to manage inconsistencies, they are manageable. There are well-known ways of managing inconsistency. When we are developing, for instance, requirements for a software system, you're going to have in a large system tens, hundreds of conflicting requirements, and then you have techniques to solve these requirements that are based on logics for inconsistency, for instance, right? So yes, it's a welcome question, but it's another application where I see a benefit of integrating techniques. If I miss the question, you can ask me the question directly later. Yeah, if I missed it.
Luis, yeah, if that's a good reminder. If you have time, maybe jump on Discord and see if anyone wants to follow on with anything. So you mentioned modal. Oh, is there another?
Yeah, just one more question just appeared.
Yeah.
We have seen a lot of talks about learning and reasoning, but very few about knowledge and therefore knowledge representation. At the old times of expert systems, we used to build knowledge bases. In your view, knowledge representation in a symbolic fashion still relevant?
Yes. The more knowledge I have, the better it will be for the future. It's clear that we're going to have fully integrated systems. If we have organized knowledge, that's extremely useful for this integration. So knowledge representation is key. I came from some background in this area as well. And the way that we perhaps, I mean, the idea that we had to develop, connectionist, modal logics, temporal modal was exactly because we came from knowledge representation, right? And we do not oppose the use of integrated techniques. We are not saying that logic is useful and neural network is not. We are saying both are useful. And we always said that, and that, I don't know, some people don't like it. I don't know why, but some people prefer division. I prefer integration and composition. Computer science is about composition. It's not about division. So I think it's extremely relevant because if you have massive amounts of knowledge, well-organized knowledge, the task of inference and learning and doing useful things is going to be much, much better realized.
Very good.
Alex, I have one more question from my end.
Please.
So, Luis, early in your presentation, you mentioned learning from environment. Like you showed this picture of your daughter, like cleaning teeth for your doll. How do you think it's different from RL? RL seems to be like an attempt to learn from environment. So when you mentioned that neurosymbolic systems need this, what is the difference from what we have in it?
Yes, in RL you have the let's say the reinforcement process that sometimes is restricted to the specific kind of information. If we have an agent that has to learn spatial information, temporal information, uncertainty, right? Contradictions from the environment, how to manage contradictions. So we need something that goes beyond. RL is very good for very specific applications. What I'm trying to make the point is that to have a fully operational agent in an environment and not collapsing in an environment, right? It cannot be only pre-trained in specific tasks, right? In narrow tasks. It has to be richer. So building a system that integrates space and time and uncertainty in a sound way that never makes mistakes, like an autonomous car, it's extremely hard. It's extremely hard. And so the showing, if RL was the only solution, the cars would be on the street with no drivers these days because people would have figured that out. But it's not the case. Unfortunately, it works in narrow domains for narrow applications, very valuable applications, do not get me wrong, right? But you need to go beyond.
Okay. I think we're at time, but I'll wrap up by saying that a lot of the things Luis talked about, you'll be seeing more of, because many of the ideas he mentioned are deeply integrated into the Institute's own work, research work. So you'll be seeing new instantiations of Luis's groundbreaking work on modal connectionist. We probably won't use the word connectionist these days, but same idea. And knowledge representation, by the way, we will be showing a specific powerful kind of knowledge representation. This is actually part of the work that I mentioned on the protocol, Neurosymbolic protocol. So those of you interested in knowledge representation, that's a big part of what we'll be getting into in that work. It also was a good a suggestion in a sense. I didn't realize we haven't covered knowledge representation enough, so thank you for that. So we'll maybe invite more people to talk about knowledge representation issues. Luis mentioned the course that he gave some notes on in a recent dog stool on Neuro-Symbolic AI. You'll be seeing the fruits of that in the learning site soon. Luis is on our Institute Education Committee, as is Olga. And also, Luis, I thought a very good point Luis made is about having underlying scientific principles for a paradigm in a technical kind of framework. So, and that's one of the complaints kind of about neural nets. There are principles, but it is hard to understand the resulting model. So I think and other machine learning paradigms arguably had sort of stronger ways to analyze models, support vector machines, and so on. So so you'll be seeing a lot of that kind of work, a very mathematical work, as well as very practical tool work coming up from the Institute and things that we select kind of for presentation. So as always, please suggest other things that anything you want to see presented. Suggest yourself as a presenter if you want. Present an old paper or something new. And Luis has seen it all, so he's the guy to ask on big picture questions. Also, intricate questions on. We didn't really get into modal logic, but I'm sure some of you will have intricate questions on these kinds of things. But Luis is part of the Institute, so he'll be around in general. So thank you so much, Luis, and please let's continue the conversation on Discord.
Yeah, just let me thank you. Yeah, that
Very
yeah.
I
just want to thank you. No.
Yep.
In a strong. Oh yeah, thank you, Alex. Thank you, Olga. And I think it's very good to be here. And Alex, you're leading a great effort in terms of showing that you need several tools to solve a very complex problem. To solve AI, you need more than one approach. And I think that's this series and the work you're doing is a fantastic work for that. Towards it. Thank you.
Alex, on the topic of presenting papers, I think Luis mentioned a few very good candidates, like papers covering different approaches for combining neuro and symbolic. So I do think that presenting one of those papers could be interesting for the community, like as an example of different neurosymbolic approaches, so that we all discuss at least one candidate from each of 6 types.
Yes, it's very good. I think actually that's a good segue to Parisa next week. She's going to cover some of these frameworks. And then we'll eventually march our way through everything that Luis mentioned. But I think thanks for that excellent overview, Luis. I think a lot of people have been wanting to see this. So let us know what else you want to know about. And we'll see you soon. See you next time.
See you.
Take care, everyone.
Bye.